Hello, welcome back to the part 2 of the series, which is embedding deep dive. In part 1, we learned about what is embedding, why embeddings are used, different types of embedding, when to use each embedding type, and different embedding applications in LLMs and RAG and other systems, right? Now, in this series, in this session, we are going to actually deep dive into embedding by building a mini embedding model by training the model on a small document, right? With that, let's get started. So before we actually get into the code where we train our embedding model, I would like to walk you through about word2vec. So the foundation that made this modern embedding possible. In this session, we'll go step by step, not just talking about the word2vec, but truly understanding how it learns a meaning from the context. So we'll start with what is word2vec is, how machines convert words into numbers that capture meaning. Then we look into a bit history of why the 2013 Google paper was such a breakthrough in the NLP, right? Next look we'll go into each layer and see how it actually works, the intuition behind the word to vec and then its architecture that trains the embeddings, and then we'll go hands on. We'll train a small word to vec model from scratch using a pdf called bad ideas about writing. You will see embedding emerges as the model learns the context. And finally, we'll query our model to show how it understands the meaning, the grouping related words and the concepts together in the vector space. So by end of this session, you won't just know what the embeddings are, you know how they're actually created, why they work and how to build the one by yourself. So first let's start understanding what the word to vec actually is. So before the word to vec, computer treated every word as a completely separate symbol. Cat and dog had no connection, between them. From the computer standpoint, they were just two different IDs in the vocabulary. That's what the word to vec changed. It is a neural network that learns to represent word as a vector, a set of number that captures meaning through the context. For example, the word cat and dog often appears in similar contexts. They both occur near words like pet, food, or sleep. The model learns that the pattern and pulls their vectors close together. The result is that the words that share the same meaning like cat and dog end up near each other in a geometric embedding space. So each word now point in that space represented by a numeric vector, right? So what is important or maybe what is powerful about that is that these vectors don't just represent the word, they encode the relationship. They can perform operations like king minus man plus woman equal to something close to queen. So that's the essence of word2vec, teaching machines to understand the relationship between the words, not just memorize them. So before word2vec, we use technique like bag of words or TF-IDF. Those captures how frequently the words are appearing, but not the meaning. Then in 2013, a Google research team introduced word2vec. It is a learned, dense, low dimensional embedding that preserved the relationship between the words, something no model have done efficiently before. This single idea reshaped the natural language processing, powering similarity search or maybe clustering or analogy reasoning. It also laid foundation for everything that followed, whether you are talking about BERT or maybe fast text and ultimately the LLMs we use today. Now that we know what the word to vec is and where it came from, let's see how it actually works. Imagine we start a simple sentence like the cat sat on the mat, the dog lay on the rug. The model doesn't know what a cat or dog mean. It only knows that they appear near certain other words. So word to vec slides a small context window across the text. For example, if the context window size is 2, the center word is cat. It looks at the word around it like the, sat, and on. So each of this space, cat, the, cat, sat, cat, on, becomes a tiny training examples. The model goal is to predict which words are likely to appear near a given word. So if cat often appears with the mat, their vectors gradually move close together in the embedding space. So over time, trying the models and millions of these tiny predictions cause the vectors to arrange themselves into a meaningful map where the words cluster together and unrelated ones drift apart. So that is the magic of word to vec. It learns meaning purely from context with no definitions, no grammar, and no supervision. Just patterns in how words co-occur, because you are exposing that model to millions of sentences. It is seeing every time the dog is coming, I'm seeing that, or cat is coming, I'm seeing that, mat is coming. Every time we're talking about animal, I see the dog. Every time I talk about zoo, I'm talking about lion. Every time there's a forest, there is some different meaning. Every time I talk about the road, we're talking about the car, train, car, bus, or something else. Every time I talk about the sky, I'm talking about aeroplanes. So it knows that by looking at all these things, it will understand the meaning. Now it knows how the words are grouped together. So word-to-vec architecture is, surprisingly simple. It's just a small feed-forward neural net with just one hidden layer. The input layer represents the current word as a one-hot vector. All zeros except a single one, if you know one-hot encoding, all zeros except the single one for the active word. That vector multiplied by the first weight matrix, this instantly select the corresponding row of weights, which becomes the embedding for the word. The hidden layer passes through that embedding to the output layer, which predicts which words are most likely to appear nearby. During training, errors are propagated backwards, adjusting the hidden layer weights until similar words have a similar vector. So after training, we discard the output layer and keep the hidden layer weights. Those are the embeddings we'll use for semantic similarity. So word2vec actually support two ways of training embedding. The first one is continuous bag of words. Here the model looks at the context words and tries to predict the missing center word. For example, if you give the dash sat on the mat, it learns that cat often fits there and then produces a cat. The second one is skipgram, which flips the direction. Now we take the centered word, say cat, and try to predict its neighboring word like the, on, and the mat. So CBOW is faster and works well for a frequent words, while a skipgram is slower but better for a rare words because it learns richer representations. So but regardless of which model you use, the both approaches pushed words in similar contexts close together in the vector space. So let's look at what happens inside a word to vec during the forward pass. This is where the model predicts which word are likely to appear near a given word. We are going to see this in action in the code, but let's understand the concept. So we start on the left with our input word cat. The model doesn't understand text directly, so we first converts cat into one hot vector. You can think of it like a long list of zeros with a single one marking the position of a cat in the vocabulary. This one hot vector is then multiplied by the first weight matrix W1. This operation simply selects one row from the matrix. That row becomes the embedding for the cat. So for example, it might come out like 0.2 minus 1.1, 0.46 like that. Next, the embedding is passed through another matrix W2, which produces score for every word in the vocabulary. So after applying the softmax function, those scores becomes the probabilities. Finally, we get predictions like the 0.28, on 0.21, mat 0.18, and so on. This tells us that how likely each word is appear near the cat. At this stage, model is just predicting. It hasn't learned yet. The real learning begins when we compare these predictions with the true context words and adjust the weights. That's what we'll explore next in the backward pass. Now that we have seen how word to word predict the context during the forward pass, let's explore how it actually learns. So again on the left we see that the probabilities. For example, the model thinks that the word the, on and mat are most likely near to appear the cat. These probabilities come straight from the softmax layer where we have applied the probabilities. Next, we have the true context which is automatically derived from our sentence. In this case, the cat sat on the mat. So the real neighboring words for cat are the, sat and on. The model now compares what it predicted versus what actually true. The difference between these two distributions in typical neural networks what we call loss functions, right? So you can think of this as a model measure of how wrong it was. The error is then sent backwards through the networks. This step is called backpropagation. In backpropagation, we see like which award the how these weights have contributed to this error. So during this process, both the weight matrices W1 and W2 which we saw previously are adjusted slightly to reduce the error. We'll again pass through this. Then this process repeats thousands and hundred thousands of times, and these small updates accumulate. And then by end of the training, words that appear in the similar context like cat and dog gradually move close together in the vector space, while the unrelated words like a banana and cat, maybe car and cat might start drifting apart. This is how the word to vec learn meaning, not by memorizing but by continuously refining its internal geometry to mirror the way the word co-occur in the natural language. So we discussed this in the previous session, but let's also go into this concept again. So every word embedding is just list of numbers, right? For example, here we have the vector called cat, where we are saying it might look like 0.12 minus 0.45, some random numbers like 0.078 like that, right? List of numbers. So here each number represents a hidden dimension that the model has learned on its own. Maybe one correlates to with being alive, another being an animal, another maybe with a size, right? So none of these access were hand labeled. They emerge automatically from co-occurrences patterns in the text. When two words share similar pattern, their vector align. That's why the cat and dog end up close together, while the carrot and banana end up close together, right? Maybe they are far away. So these numbers through the abstract encode the essence of how words behave in language. That is what makes embedding model more powerful, and that is why they are the foundation for everything from search to LLMs. Next, before we finally see this in action through a code, let's summarize. Now that we understand what embedding represents, let's see what happens when we look at all embeddings together. So word to vec doesn't just learn one vector, it learns one for every word in the vocabulary. Each word live in a high dimensional space, usually 100, 200, 1000 dimensions. Of course, we can't visualize that directly. So we use a dimensional reduction techniques like PCA to project these vectors down into 2 dimensions. When we do this, you will notice a pattern. Words naturally form clusters based on the meaning. So we'll see that actually when you do notebook, we will definitely see this in action. Like cat, dog and lion come together as animals, Apple, banana, orange group as a fruits, Paris, London, Tokyo as cities. So these clusters are not hard coded. They emerge purely from how words co-occur in real time. That's the beauty of embedding. You are not training it. It is basically going through every document, every line, every word over a period of time after going through millions of day web pages or documents. It learned the pattern like how these words are grouped together. So this is a geometry of meaning and what makes embedding such a powerful foundation for for everything. So this is the notebook we are going to use. So to start with, we'll install some libraries, especially the one I want to talk about, Gensim, which is used to train any word-to-vec model, and we use PDF Plumber for the, for PDFs. So let's install all these libraries. So it might take some time to install all these libraries. So now it has installed all the libraries. The next one is we need to download this PDF file and then extract the text from PDF file and then tokenizing the sentences to create a sentence tokenize which will form our training data where we train the model, right? So what I'll do is when I run this, you can see that it is actually going to download the PDF. Now it is extracting the text from this PDF. Because there is a 300 pages text, it will extract all the text and it will convert this PDF into the sentences. So it has extracted this text from this one. You can see some sample sentences. So it also created this sentences.json here, which all the sentences in this particular PDF file, right? Now this is our training data is ready now. Next we are going to the tokenize these sentences. Right. So after we do that, we are just going to print a simple statistics. So some of the top 20 most frequent tokens here are the and of and all the things. So it just printing some simple statistics. Now let's understand this word-to-vec model. So now we are trying this word-to-vec model with, as of now, of course, typically your embedding models will be like thousands of dimensions, but we are using only 100 and then we are training on 24 epochs with the window size of 5. As I told, window size means like how many words it looks in the before and after from the center words, right? So we are using that as a 5. Now it might take few minutes to train this model because it has to go through each and every sentence to create that embedding, do the loss, compute the loss, and then eventually we'll have the and then after that we save the model into some, and then once you save the model, that's where we actually start executing, giving some words to it and seeing how it understands the relationship. Now this might take a few minutes to complete the training. So it started. So now you can see the epoch 1, 2, 3. So it might take few more minutes to train this model. So now it has completed the training of this, this model, this one. Now let's first go and see how the embeddings are generated for a few words. So I'm having writing, students and teachers and language, and of course I want to show that the sample data it is still using the same sample data it is using, and then this is the, of course it is not showing all dimensions, it is showing only the first 8 dimensions of the word, right? And then of course you can see that you can increase it to say 100 also. It shows all 100 dimensions entire vector for each word. Okay, to keep that means this is particular word teacher is represented in so many different dimensions. Each number means something. Okay, right? Now we'll see the similarity calculation. So we take two words, student and teacher, and then we'll see the words which are most similar to these seed words, right? So you can see that now, of course this is based on what it has learned in this text, right? So you can see the teacher and maybe the grade, stereotype, commenting, scaffold, training, these are all coming together. That means wherever teacher is there in this PDF document, these things are coming closer. Of course this kind of embedding we are doing might not represents 100% correct, because it's learning only in the small PDF document. If you make the same thing to learn on millions of pages, maybe it will learn more meanings, but as of now we limited our model to learn only from a 300 pages PDF document. So you will see that the similarities might be real, but in case of student it performed really well. It can see that a student and rigorous rubrics, praise, all these things are coming closer to each other. Now we'll see how we'll see why. If you see in this case, Somers, we'll see. Next we'll do another experiment. We'll see like why student and Somers, whether they are next to each other, or why, what is similarity between both of them, right? So let's do that simple test. Now you can see that the top neighbors of Somers are Nancy, Macmillan, sponsoring and everything. So the shared neighbors, up the reason being, the Nancy Somers is famous for research on students revision process, how students respond to feedback, student writing development. So now we can see that these two words are appear together. Wherever you have a Somers, you will have a student also, and it tells you like what all the sentences that it has actually, where it found that both the Somers and student are together, right? So next we will test based on some some analogies, like if it is formative for summative and what is for feedback, right? If it is synchronous for asynchronous, what is online for, right? So whether if it is summative or feedback, negative, it is a formative. So both are, we'll see the rationale for why they are rational. Now we'll see how the model predicts this formatives. Now you can see that if it is formative for summative and feedback is for results, it has come as evaluation, which is 0.62%, grading, which is 0.5, because it is seeing the relationship between the way formative relate to summative, what is something relevant to feedback. Now we can see it is able to it is able to connect that the feedback and evaluation are actually same. Feedback and grading are also related, feedback and criteria related, but feedback and frame and labeling is also related. Similarly, but I'm just wondering, this is what is kind of interesting. Synchronous or asynchronous related, but how it is giving online to massive or heavy, maybe I think depending upon, maybe somewhere else it has actually seen these words close together in the corpus, in the sentence what we are having, right? So similarly you can see that a peer to feedback and a teacher to, it is saying grade. Of course it makes sense, grading makes sense, summative makes sense. I'm not sure why select stereotype, maybe it is there somewhere in the document which are very close together, right? Similarly, so what do we, the basically what this is, what it is we are trying to showcase here is that whether the model is able to find the similarities based on the association, how it has seen the words, the frequent co-occurrence patterns in the corpus, right? Next we will compare multiple concepts for the semantic similarity matrix we'll build. And let's see that. Of course, I'm not walking through the code. We'll see only the result, because the whole idea is to see that how these models are related. So now we can see that semantic similarity, feedback to feedback, obviously one. You can see that feedback to formative is 0.72 similarity. You can see that this is a feedback to point, formative. Where is feedback? Here, right? And then you can see that feedback to format is 0.73. Similarly, summative to evaluation is 0.8, or grading is 0.73, right? So feedback is 0.62. That means it is whether it is able to correctly map the semantic similarity between different words. And next we'll see the to test if the model can identify where the words which word actually doesn't fit in the group. Like, we are giving the feedback, formative, summative, evaluation, student. We expect that the outlier in this is student. Okay, the reason being all are assessment term except student. Now if we say writing, revision, editing, grading and draft, here grading is outlier because all other are writing processes steps next to the grading. Right, now let's execute this particular cell and see how it fares actually. Now we see that all assessment term except student. Now correct, the model correctly identified the student. It said that feedback average similarity is 0.59, formative anything above 0.5 is very decent, this one. Now you can see that in this one it didn't do a good job. All word writing process steps except grading, expect outlier grading, but model identified draft as the outlier. That means it didn't perform really well on this set. Next, it has performed well on this Havet, Somers and online ants, and all of them are words, but it identified that online is the outlier because rest of them are names, but except the online. Now let's see, it did a good job on this one. Synchronous, asynchronous, teacher, online. So obviously teacher is outlier here. It is able to identify our teacher outlier because of the, you can see that average similarity is only 0.372 here, right? So again, it doesn't say anything bad or wrong. It just sees what is similarity. You can make a decision based on that. Now you can see that we are giving a peer, teacher, feedback, tutor and feedback. So the outlier is feedback, but the model identified wrongly here. It identified teacher. If you see that for teacher it has given 0.375 and feedback it has given 0.44 similarity, which is not really true. But maybe it all depends upon how the kind of the quality of the text we have used. Of course, this is only a demo model, so we have used a limited number of text. There could be a lot of mistakes in the choice of the document we have taken. But the same model learned on say 50 more documents, it knows that it simply starts moving this vectors away, because now it knows that the outlier is feedback, not a teacher. Next we explore the neighborhood words. Okay, so what is this is that this explores in what neighborhood each word lives in, so that gives you the context of how they appear. So now let's see, now we can see that we have taken few words here, the neighborhood feedback. So very close is formative and tips, and close is evaluation summative. I think this is doing good job on this. Okay, right? But next look at the neighborhood student, and what are all the words are coming close? Extensive, student, praise, load, moderate, evaluate, rigorous, rubrics, evaluation, jargon. So moderate coherence, for basically around 0.49 mixed context. Now we'll see the neighborhood online, which are all coming close. Because the reason being it contains a lot of researcher names, because the academic citations which they are having, and then there is a revision. Contains some assessment terminology, right? So that's where it is having a moderate coherence. So now let's look at the semantic journey. What is semantic journey is, how does the the find the path between two distance word by following a chain of semantic association learned from the corpus. So how it works is, you start with a particular word, something like a writing, and then look at the neighbors of the writing. So are they close related to this writing? High similarity. So moves us closer target B, which is high similar to B. Now we move that word and repeat this process until we reach that word. So if you're starting from writing the technology, how can you arrive at writing technology? So path found is, writing and asynchronous are related. From asynchronous, promise, and promise to technology. So basically we are seeing the path the of the association. The semantic, this is also called semantic journey. So let's explore some of the semantic journeys of few words. Now we can see that this we'll see for one example. So a student to assessment, okay. So direct similarity is 0.365, but if you see student to evaluation is 0.485, from evaluation to assessment is 0.65. So it took 3 hops before it can reach the student and assessment associations. So an average in each step, the similarity is 0.56. So the weakest link is the student to evaluation. So direct similarity between student and assessment is only 0.6, but if you can go from student to evaluation, assessment, that's how the target has been reached, right? Similarly, you can see that writing to technology, how it has basically gone through this path. So it went through writing to physically to techno, because it is having the tokenizing, maybe a technology that has made in techno, cell phones, tablets. I think it took 6 hops to convert reach from writing technology, but the direct similarity from start to end is 0.4 to 9, and the weakest seems to be 0.64, which is between the writing and I guess between the with the writing, right? So this is the way we can actually do the semantic journey. So maybe you can explore this notebook. You can also play around along with in this notebook. So to summarize, what it means is that we have explored how we can actually train a simple model, simple PDF document on the model, and we have explored the relationship between the words using that. Of course, this is very a simple PDF document. It is not really close to perfection. I just want to show you that basically how this is being done. To summarize, basically when you train the model on this large PDF text, over a period of time it is seeing that how these words are related together, and then the vectors will group naturally close together.